Recording is rolling. Welcome to a new week, Monday, April 4th. So this week's gonna be kind of a weird week. Here, you guys come here. It's kind of a weird week. So you guys know last few weeks we've been doing things like thermodynamics, materials, had you guys make a sieve. And so today's kind of the last day on that. We're gonna do a Kahoot. You guys are gonna get to see, I'm gonna see what you guys remember or what you guys can apply. You guys gonna see some Archimedes principle, Bernoulli principle, Pascal principle, those type of questions. All right, then next couple of days, I did want to do something with astronomy with you guys, expose you guys to some astronomy. So I found this series of videos on Crash Course. They're like 40 or 50 of them. I went through and I picked out 8, so it's gonna be a couple days. I mean, they covered topics better than I would be able to lecture to you guys myself. So be a little bit different type day. Went through and had to make some hard cuts, but I found some ones that I think are pretty good for you guys, pretty worth your time. So that'll take a couple of days. Put together some materials about that. And then the next main topic that we're going to do that's going to take a few weeks to do is going to be electricity and magnetism. So we'll really start that this Thursday. Give you guys some notes tail end of this week, and then we'll go to that. All right, so let's get this Kahoot rolling. Switch screen over. Oh, hold on. Sorry about this, guys. Yeah, go ahead. I know this is messed up. Here, let me fix this. Okay, hang on. Okay, I know you guys want the code. I just have to do this weird switch thing. All right, so the 7-digit PIN is 5742339. All right, yeah, this looks better now. All right, we are back. All right, you guys ready? Let us commence the battle of the bins. Density is defined as mass per unit volume. Good call. That might be kilogram per cubic meter. That might be gram per cubic centimeter. Okay. Mass per unit volume. Hey, what would happen if you take a solid block of material and cut it in half? What happens to its density? There you go, unchanged. And so when you cut something in half, some things change about it, some things don't. Its mass would get cut in half, its volume would get cut in half, but the ratio of those two would stay the same. Things that stay the same, you can call it intrinsic property. So its temperature would stay the same, its density would stay the same, its color would stay the same. Right? Intrinsic property of that material. Less force is required to poke through an eggshell. Which way? Less force. I'm going to break that eggshell. Yeah, good call. All right, so the physics perspective, remember one thing we were looking at was arches. Told you guys one of the strongest shapes you can create is like a catenary arch. Right? So catenary, easy to make, you hang a chain, form a natural catenary. And then if you stiffen that, turn it upside down, you have a really strong arch shape. So if you put a load on top of the arch, well, it'd be kind of like trying to break into an eggshell, right? Hard to break it that way, but poke it from the other side, not as much tensile strength. Kind of analogous to how concrete has a huge compressive strength, but a very weak tensile strength, not very much tensile strength. There's also an evolutionary biology perspective on this too. Like, how did the egg come out to be so common in nature? Well, the egg would be something that you would want to be very difficult to break into, but very easy to break out of. Ooh, right? So that's like a biology perspective. Ben, move into the top. Right ahead of Ben. Which geometrical shape has the least surface area for a given volume? If you want to minimize surface area. So you had some like Play-Doh. Which one of those shapes would be the least surface area for that Play-Doh? It is a sphere. It is a sphere. So, yeah, and a couple of guys chose the pyramid. I think out of those options, the pyramid would actually be the most surface area for that particular shape. Right, so there's also you asked I think you would call it the converse of this. How can you maximize the volume given some surface area constraint? Maybe the way question is phrased is a little bit easier to think of. But what I'm trying to tie this into is there is a similar two-dimensional question. I mean, this is a three-dimensional question, right? But in 2 dimensions, you guys ever got the question? You guys ever seen the question? If you have some amount of fencing material, let's say you want to build a fence. Like, okay, well, I got so much money, so I'm going to go buy all this fencing material. Is that, well, I want to enclose the largest land area that I can with my limited fencing material budget. What shape fence would you create? What shape fence would you create to enclose the largest area with a limited fencing material?
A sphere.
How about in 2 dimensions that would look like a circle? Yes, a circle. A circle will do it. Right? And now, if you were constrained to make some kind of rectangular shape, then the answer would be a square. But yeah, more generally, the answer would be a circle. Yeah, the closer to a circle you create, or in 3 dimensions, the closer to a sphere. Right? All the properties are kind of analogous. Now, what branch of math can you use to prove this? Well, you guys see that word least? If you ever see least, most, or optimal, then the branch of math you need is calculus. Calculus you can prove. So yeah, if you guys ever take a calc class, look for that question. Probably a fence question. You'll probably see some version of that. This determined snell. Move to the top. If all dimensions of a house were to double, right, so twice as wide, twice as deep, twice as tall, what would happen to the floor area? It would go up by a factor of. Yeah, factor of 4. And so twice as wide, twice as deep, right? Okay, so you need 4 times the floor tiles. Like if you needed 1,000 floor tiles, now you need 4,000 floor tiles. Right? The height change of the house doesn't really make a difference to the floor area, though, right? How about this, guys? We're doubling linear. We're increasing the house linear factor 2, right? So twice as wide, but also twice as deep and twice as tall. Right? So what if you were to walk around the perimeter of this new house compared to the smaller house? So the big house compared to the small house, how much further would you have to walk around? That'd be increased by a factor of also 2, right? It'd be twice as far around because you would step that off in some number of meters. That's like a linear way to measure. And so yeah, this particular house would take twice as far to walk around the perimeter. Hey, how much paint would you need to paint this house compared to the small house? 4 times, because paint is like a surface area. So floor area, surface area, anything that's like square meters, right, is linear factor squared. So 2 squared is 4. Right? Hey, what would the volume of the big house be compared to the small house? Volume. That'd be 2 times 2 times 2 is 8 times. Every 8 times is voluminous. Ooh, right? You guys see that scaling poster up there, right? There's this phenomenon in nature where the larger the animal, obviously the more food it would consume. Like an elephant consumes more food than a mouse, but there's actually less food it consumes in proportion to its own mass, right? So like if you were a mouse, all you'd be doing is just like eating food all day. Then the larger you are, like elephants don't consume as much food in proportion to their own mass, say even as much as we do, right? And that probably has something to do with this phenomenon here, because when you scale up in size, you think, okay, well, I have blood cells delivering oxygen to all parts of my body. That's sort of like a surface area question, like surface area, like the arteries inside your blood vessels. But then let's see, your volume, your mass would go up by linear factor cubed, right? So these different proportional increases. Determined snail still keeping the lead. Alicia on fire. Up. An elephant that grows to twice its normal height. We'll see its weight increase by a factor of what? So twice as tall elephant weighs how many times as much? Yeah, it's 2 to the power of 3, right? Because not only is it twice as tall, it's also twice as wide and twice as long, right? So I would say its volume would go up by a factor of 8, right? 2 to the power of 3, 2 times 2 times 2 is the answer, 8, right? And since mass occupies volume, it would be 8 times as massive, right? And then therefore 8 times the weight, right? Like I said, what about this though? What if you had a couple of circus elephants? One was twice as tall as the other, and you were going to paint these circus elephants. How much paint? How much more paint would you need for the twice as tall one compared to the small guy? That answers 4, because paint would be like a surface area, right? Right? You need 4 times the paint. 4 times the paint for 8 times the weight for twice the height. There you go. Oh, Licha, move into the top. Help spot. Where is the pressure greater? 1 meter beneath surface of Lake Michigan, or 1 meter beneath the surface of a pond? Or is it the same? Where's the pressure greater? It is the same pressure, And you know what? I'm not 100% sure whether or not I actually showed you the relevant equation this last week, although I showed you somewhere once, so flash this up here real fast. Okay, here we go. All right, so here's the relevant equation that would have helped you answer that. The water pressure, what is it equal to? Well, it's equal to rho GH. Rho is the density of the water, so let's call it 1,000 kilogram per cubic meter. G is the gravity field you're in, so 9.8 or 10 meters per second squared about. Right? And H normally stands for height, but in this case, like depth, like how deep are you diving into the water? So we can actually run a calculation on that exact question. And the answer was the same. So it doesn't matter how voluminous the body of water is, just how deep are you, right? So we got 1,000 kilogram per cubic meter times 10 meters per second squared times the depth of 1 meter. Wouldn't that be like 10,000 pascals? So if you go deep down into the swimming pool, you feel an additional 10,000 pascals. Well, 10,000 pascals in addition to the pressure you feel right here, which is about 100,000 pascals, right? Something like that. How about a similar looking formula that I know you guys did see last week was this right here. Guys, this is what principle? Whose principle? Archimedes. Yeah, that buoyancy. Archimedes. Good call. Okay. Remember, Archimedes' principle, you could say it's the buoyant force is equivalent in magnitude to the weight of the displaced water, but weight of displaced water. Let's say that's mass of water, not mass of the object. This is not density of the object, this is density of water. So density of water times volume of displaced water, that's the mass of the water displaced, times gravity field. That's the weight of water displaced. Okay. Got a diagram for you guys here, put this all together. Okay. So say I have a block floating on the top, well, equilibrium. It's got a weight down and a buoyant force up. And those two are equivalent magnitude. so it can balance out. Okay. What if you have an object that's sinking down into the water? And I'm showing this here in the process of sinking down, right? Now this is going to sink down all the way to the bottom. It can't just like stop like partway between, it should go all the way to the bottom. Okay. But I put some trying to either, you can think of these pink arrows like either force vectors or maybe like magnitude of pressure. Either way you think of it. Okay. You see how these arrows on the bottom are like twice as long as the ones on the top. Now, why I draw them specifically twice as long? Because the bottom of this object is twice as deep as the top of the surface of the object. You guys see that? Twice as deep means twice the pressure because there's a linear relationship between these two. Go twice deep, get twice the pressure. 10 times as deep, 10 times the pressure. You guys see that? Okay. And then you guys see how the pressure and for the force per unit area would increase going down? Okay. Okay. Now, as this object sinks to the bottom, the proportion would change. So it's not always going to be like a 2-to-1 ratio. But the difference in pressures and therefore forces would actually stay the same all the way down, so that the buoyant force would be the same regardless of the depth of the object. Okay, you see that? Let's switch it back over. All right. Got it. Oh, determined snail. Ooh, in and out. Alicia. Water pressure on a submerged object is greatest against. Yeah, the bottom of the object. All right, we're gonna switch over so you guys can see my picture again. Okay. Why is the water pressure greatest against the bottom of the object? So, yeah, you guys see the submerged object, like as it's sinking. No, I didn't draw all the forces on this guy because it has a weight that's obviously overcoming the buoyant force so that it can sink to the bottom. Well, I mean, but yeah, you guys see there's more pressure and force on the bottom than the top. Right? In fact, that pressure would be scaled linearly with the depth. That's what this top equation says. If you're twice as deep, you're going to get twice the pressure, right? I see the bottom surface is twice as deep as the top surface, right? That means twice the pressure on the bottom compared to the top. Deeper you go, the more the pressure. And the fact that there's more pressure on the bottom of an object than the top means that the direction of the buoyant force is up. That's why the buoyant force pushes you to the surface of the swimming pool. Snail points. Archimedes' principle says that an object is buoyed up by a force that is equal to what? Yeah, the weight of the fluid displaced. Okay, so I just went over that too, right? Right, so rho GV, right? So density of the fluid times gravity field times the volume displaced. That isn't being the weight of the displaced fluid. Actually, I've got another perspective for you guys on this one. So opportunity to switch over and show you guys this anyway. Okay. Okay. So here's the equation that goes with this. Density of water times, remember, this is not the density of the object, it's density of the water or the fluid, right? Times volume, that's the mass of the fluid, times G, that's the weight of the displaced water. It's like, for example, this floating block of wood here, this Hatch-Gen volume, if you were to fill that with water and weigh that water, that would be equivalent to the buoyant force, right? Or how about the object that is completely submerged and sinking? Well, same story, and that buoyant force would be less than the weight of the object, so it could sink to the bottom. Okay. But here's another perspective on this. Do you guys remember there's a Paul Hewitt video where he demonstrated this with some scales, right? Where he took an object and dunked it into water, and then since the water was filled to the brim, that displaced some water, and that displaced water was routed through this straw, and he captured it in this beaker over here. And he looked at the decrease in the force reading on the scale due to dunking in the water, right? Because now there's it did submerge, right? Its weight overcame the buoyant force, but the string tension lessened because there was that additional support force with buoyant force. So the scale rating went down. Okay. But the captured water over in the beaker, well, the beaker itself weighed some amount, but that captured water increased the force rating over here. And in fact, it increased it exactly by the amount of the decrease in force over here. Right. So that is another perspective on Archimedes' principle. Buoyant force is the magnitude of buoyant force is equal to the weight of water displaced. Yep. Oh, then hopping in the top 5 twice. 2 equal-sized buckets filled to the top with water. One of the buckets has a piece of wood floating in it, making its total weight okay, yeah, it does turn out it's the same as the bucket without the wood floating in it. I probably should give you guys some more time for this one. I think this one takes some deep thinking. So let me definitely switch over and show you guys what I'm talking about here. This. Here we go. All right, so the question was between these two. Say these are both filled to the brim with water. Only the one picture on the left has a block of wood floating in it, right? So I guess the volume, the total volume of the one on the left is actually more than the volume of the one on the right. Is that because it's got the wood floating in it? Right? But these both weigh the same. Now, why do they have to weigh exactly the same? Right? Well, what if you froze time and then you pull this block of wood out and then there was a void right here and you fill that void with water and then you like weighed the water that's just in this hatched volume area. Right? Well, the weight of that water would represent this here buoyant force, which you guys see right here because of equilibrium is also equivalent to the full weight of the block of wood itself because it's just floating there in equilibrium. So that means that these two situations in terms of the total mass and weight are equivalent to each other. I just made up a number like 100 newtons, but they would be equivalent. Okay? Now, what about this though? What if instead of a block of wood floating on the top, you have a block of iron? Ooh, look at that, Fe, iron. And it sinks to the bottom. It's still filled to the brim, so the water level rating is the same, right? But this block of iron sinks all the way to the bottom. Is that still going to be equal in weight to the first two, or is it going to weigh more? I think I'd say it's going to weigh more, way more. Or how about this? What if the block of iron took up almost the entire thing, and there's like a little bit of water that also happened to come to that level? Would that obviously weigh more? Yeah, I mean, one of the things you can get out of a class like this is, well, take variables to extremes. If you're not quite sure, you'll blow up the variable and see what happens. Yeah, it would weigh more. Now, again, I just made up some number. Probably depends on volumes, but yeah, sure would. But these two pictures on the left, yeah, same weight. It does take some thinking. Ooh, and moving up. Determined stale, still got the lead, 7,000. When a boat sails from freshwater to saltwater, saltwater is really dense. Okay, how will the boat float? You guys got it. So remember, buoyant force, rho GV, where rho is the density of the fluid, and saltwater is more dense than freshwater, so that wouldn't create a greater buoyant force. Push the ship up, displace less water. Yeah, so the ship would float higher in the water. Does anybody here happen to, I don't know, go to the Dead Sea over in Israel? Anybody there? Dead Sea? Oh yeah, right. Were you able to actually like dive down into the water? No. All right. I've never tried this myself. Never been over there, but yeah, I'm told it's impossible. I guess you verify that. Yeah, my brother went over there and said the same thing. He's like, oh yeah, you can't, yeah, because the water's like so salty, it's so dense, you can't actually sink in that water. I guess if you could buy a tub of salt, you could try this maybe in your own bathtub. But yeah, salty water, very difficult to sink. Hydraulic press or hydraulic lift works because there's hydraulic lift work. Yeah, so all true statements. In fact, the red one, yellow one say exactly the same thing. So Pascal's principle is that liquids transmit pressure undiminished. Maybe you could say there's a little bit more pressure with depth as you go down, but definitely equal pressures at equal elevations. Right? And then the blue one brings in the mechanical advantage, right? The fact that you have different piston sizes. Right? The next question, actually, there's a picture of a hydraulic lift if you want to see one again, but you guys saw back in your notes last week. So equal pressures everywhere. Pressure is force per unit area. You can switch that around and say if the force is equal to pressure times area. So if it's equal pressures everywhere acting on different areas, that results in different forces. Ooh, right? This next question is also hydraulic lift. Look at this. Which side of hydraulic lift is the input force applied? So you're trying to lift that vehicle. So the input force is like you applying the force. Which side is the input force? Call the car the output force, right? Yeah, look at that. One was okay. So you're pushing on the small diameter, like small cross-sectional area piston. Okay. Small force divided by a small area. Okay, results in some pressure. That pressure transmits undiminished to the other side, where a large force can act on a large cross-sectional area, right? So you can lift a very heavy car. This reminds me of those pulley systems that you guys rigged up last semester. Right? Pulley systems, gear systems, levers, right? You get a mechanical advantage. Right? Now you don't get something for nothing, and that's true here too. Right? The volumes of fluid displaced is also equal on both sides, which means you have to push down a very long distance just to lift the car a little bit, but at least you can lift the car. Volume of water displaced by a floating 20,000 Newton boat. Is one winner. The volume of 20,000 newtons of water. All right, 3 of you guys chose a submarine, which I guess could be true for very special circumstances. Let's see, it's the best explanation for this one. Right. So remember, when the boat is pressing down, right, has some weight, it's displacing some water. Right? There are 2 forces in equilibrium. There's the weight of the boat down, and there's the buoyant force up. They have to be equal, right? So, yeah. So if you took that volume displaced of water and you were to weigh it, like in terms of the water to fill that void, yeah, but also be equal to the weight of the boat. It's Archimedes' principle. Alicia, on fire, moving up. Determined snail, over 9,000. How high can water theoretically be lifted by a vacuum pump at sea level? From last semester. How high can you pump up water? What's the longest straw you can use?
I remember this because I wanted to try it.
Oh, that's right. That's right. Yeah.
I still want to try it. We'll see.
Found it too long enough. Yeah. Remember 10.3 meters? Right. So why do straws work at all? Because there's a pressure difference, but there's a finite pressure. I mean, we're all under an enormous pressure right now, about 101,000 pascals. But another way to quantify that is 1 atmosphere. Another way to quantify that is like 10.3 meters of water. So if you guys ever find a swimming pool that's about 10 or 11 meters deep, and you dive all the way down to the bottom, that's pretty deep, right? That's like over 30 feet, right? About 10 or 11 meters. Then you would effectively feel 2 atmospheres of pressure, one from the actual atmosphere, and an additional atmosphere of pressure from that 10.3 meters of water. Now, if you go the other way, if you use a straw or a pump to try to pump up water, then you can only pump up about 10.3 meters. And then at that point, the pressure difference would run out. There would be 0 pressure at the top of that water. The water would actually start boiling at the top, wouldn't it? You guys remember that? 0 pressure water, it boils. Right there. All right. If you squeeze a balloon to half its original size, what happens to the pressure? Yeah, the pressure would increase. Increase by a factor of 2, right? Can you guys imagine if you're a fly flying around inside a balloon and somebody's pressing down on the balloon, making it less voluminous, make it smaller. Do you feel the pressure going up? You guys can feel that? Right, that's what this does. Okay? And it's exactly an inverse relationship. Right, so here, let's run some example numbers. Let's say like N times R times T is like, let's call it 100, right? You might have 10 times 10 is 100, or you might have 20 times 5 is 100. See, like half the volume, twice the pressure. That's also called Boyle's law, but ideal gas law encompasses that anyway. Feel F. Standing on the moon and you release a helium balloon. What would the balloon do? Yeah, it'll fall down. Now, guys, helium balloon. Does a helium balloon have some weight, some gravity force acting on it? Yeah. Right. So why, if there's a weight, if there's a downward force, why does the helium balloon take up on Earth? Gravity has evolved, right?
Helium is lighter than.
Yeah, helium is less dense than air. There's a buoyant force, right? And gravity is pulling more down on the air than it is on the helium balloon. Yeah, buoyant force. The direction of buoyant force doesn't have something to do with. Oh, and then of course on the moon there's no atmosphere, so there's no buoyant force. So the helium balloon would actually weigh less on the moon than on Earth, obviously about 1/6 as much. But there's no buoyant force, so the helium balloon would only fall down. But remember, the direction of buoyant force has to do with the difference in pressure between the top and the bottom of the object. Right? Hey, in this room, is there more atmospheric pressure on the floor than the ceiling? Yeah, there sure is. Right. How about this? If I had a helium balloon with me right now, let's say it's about 1 foot in diameter, about this big, right? Would there actually be more atmospheric pressure on the bottom of the balloon than the top of the balloon? Yeah. In fact, it's enough of a difference that if you multiply by the cross-sectional area that acts on, it's able to actually overcome the weight of the balloon plus all the materials, right? So yeah, that's a helium balloon will float because pressure increases as you get closer to the surface of the Earth. Enough of a difference, even across. Right? When a river narrows, what happens to the flow rate? Conservation of flow. Say the flow speed. Yeah, it does have to flow faster. There you go. There's conservation of flow. Cubic meters per second or gallons per minute is constant approximately everywhere. There you go. Smaller cross-sectional area, faster flow. Faster flow speed. Right? Right. And then that's going to lead to this Bernoulli principle, right? Conservation of flow directly leads to Bernoulli principle. On a windy day, atmospheric pressure, fast moving fluid. Oh, you guys remember? I bet you guys remember this. Right? Remember if I take a paper and blow a stream of air over the top? Right, what does it do? Does it push it down or does it vacuum it up? Vacuums it up, doesn't it? So fast moving fluids, isn't that associated with a decrease in pressure? Right. That's Bernoulli principle, which you can derive from conservation of energy. You guys can try this at home. Or wait, no, sorry, I'm thinking next question. Let's see, next question. Next question is also Bernoulli principle. Right, let's try this. Okay. A couple of you guys got that one. Let's see if everybody gets this last one. Here's the last one for the win. Reason a shower curtain will pull inside a bathtub during a shower. Turn on the shower, curtain vacuums in. Why? Yeah, there's less pressure inside the curtain. All right. Right, because that fast moving fluid, like that fast moving water, right, associated with the decreased pressure. Right. So you guys got that. You guys can try this. Right, so go home, turn on the shower head, and put the curtain nearby. You see the that curtain vacuum towards it. We can actually try this here too. Now, do an experiment with this door. Now that door over there I can't really do because it has that pressure thing inside, but this one is just a free swinging door. Okay. So what if I have a fast moving fluid next to this door that's pretty swing? Fast moving fluid. So I mean, it did take a test, but no, actually, I haven't tried this exactly. So we're doing an actual real experiment here. I don't exactly know how it's going to work out, but I know what the physics says it should do. Should a moving air current vacuum the door or push it away? Vacuum it in, right? Right. Let's see if this happens. Look at that. Look at that. The door's moving this way. Oh, look at that. Yeah. If you guys got a door at home, try that out too. All right. Let's see. The winner podium. Bronze. Ben. Bronze. Alicia with the silver and the gold. The scale. Oh yeah. Izzy and Otherby. Runners up. All right, nice job. Nice job. All right, so we got a few minutes left here. I've got a roll for you guys. A TED on mushrooms and materials. Close out this material section. Right here. All right, TED time.